One, two. Okay. Yeah, sorry for mix up, but hopefully now you can hear me. So again, let's try. Let's try again. Welcome everyone to Iron Will, this 30th something episode. Yeah, it's been a lot. It's been like 30 days, which we've been meeting here live on Twitch or on YouTube, and we've covered a lot of ground. And I think we actually covered, well, I guess yeah, I guess we could say that at this point we covered majority of Tagbittle. This exciting new database implemented in Zeek, which is super reliable, which is super fast, which recovers from disk corruption, is written in Zeek, and doesn't allocate memory at runtime. So okay, let's get started. What is the topic of today's episode? Well, for that it's useful to recall what we were discussing for past few episodes, and that was the LSM tree, the way Tagbittle stores data on disk. So if you recall, the big picture is this. Basic data structure is a grid, which is just a uniform grid of equally sized blocks, where each block is half a megabit. On top of this grid, we built a persistent, purely functional data structure, where essentially you take some grid block, you put some data in this block, and, well, I want this one. Put some data into this block, and if there's like not enough space in a single block to store all your data, you put pointers to different blocks. So by following this chain of pointers, you could recover all of your data. In particular, the specific data structure we use is a log-structured merge tree. Logically, it stores a sorted array of items. Physically, it is implemented as 7 layers of tables, where each table is itself relatively straightforwardly encoded sorted list of items, then a level is a bunch of tables where all the tables are disjoint, and then we have 7 layers which form hierarchy. Means that if we are looking for a particular key and we found it on, say, level 4, that means that we don't go and look at levels 5, 6, and 7, which means that you can implement mutation of this purely functional data structure by layering more layers on top. Now, this composition of layers, which table belongs to each layer, is called a manifest of LSM tree, and this is purely an in-memory data structure. So at any given point in time, Tagabidal in RAM maintains a mapping of all the tables which are on disk. But of course, it doesn't actually store the data in the table. So if you recall, the table is an index block, which is half a meg, which addresses a bunch of data blocks. So you could think about it like half a meg squared, like the amount of bytes addressed by a single table. And in memory, we store just a pointer to this index table, to this index block of a table, which is 128 bits of a checksum and 64 bits of the actual address of block on disk. So you see, like that's the ratio between data used in memory and data used on disk, which is pretty high. Now, the way, obviously, like it's good that you store this manifest in memory, but at some point you need to write this to disk because, well, if you start from 0, you have your data file, but you don't have anything in memory yet. So you need to read the original input from the data file. So the way this structure of layers is stored in the manifest is as a sequence of events where each event is an addition or a deletion of individual table to a particular layer. So at the startup, Replica reads these logs of events, applies events sequentially, and ends up with the same manifest which it had before it crashed or orderly shut down. Okay, I guess another component which is important to keep in mind about this picture is that the way this thing evolves is by going through a sequence of checkpoints. So obviously we cannot manipulate data in place because that wouldn't be safe for crashes. Like if you crash in the middle of an update, then your data is garbage and you cannot restore. So whenever we quote mutate data, what we are on disk, what we actually do is that we write new data in 3 blocks on disk and maintain a root pointer, an updated root pointer to like this root of new data. And periodically at the checkpoint, we go and swap this root pointer. This root pointer stored in the superblock. Superblock is the root of a data structure, so it is the single place on disk which isn't pointed to by some other pointer and checksum elsewhere. So to make superblock storage reliable, we just duplicate it 4 times at different places in the disk. Okay, so that is roughly the outline. And well, to come back to the last video, what we were discussing in particular is the process of compacting the manifest log. So this manifest log is a log of events which describes the structure of a manifest, and some events are redundant. So if you have an addition and a deletion for the same table, you could just collapse those 2 events to nothing. And because you always add and delete tables, eventually this log grows and you do want to have this collapsing of events. So that works like relatively straightforwardly. We read old manifest blocks, we discard all events which are no longer relevant, and we write smaller set of still relevant events at the front of a block. And that process is called compaction because, well, we take the same data and we compact it, meaning that logically the data remains the same, but physical representation is more compact. And this was sort of like a warm-up before the real compaction of the LSM trees. So in this episode, we kind of like start to move closer to the real compaction. But I realized that it wouldn't actually make sense if I explain compaction from the middle. So I'm going to explain compaction from the very start, from the state machine where we do some mutation of data, and we'll see how that mutation eventually propagates and ends up in some data block on disk. But to do that, I need to explain you target-middle object relational mapper, quote, quote, ORM, which is kind of like two things. First is just the abstract idea of how you could use LSM trees to store objects. And the second is crazily complicated comp time Zeek code, which allows us to declaratively maintain this value. So let's start. And let's start with the very beginning, target-middle.zig file. So target-middle.zig file, if you have already for some reason forgot our first or second episode, is the file which describes our data model. And our data model is stupidly simple. We have accounts and we have transfers. Those are compact data structures, densely packed. So you see, we have external struct here, which means that we think about this not as logical, as a set of fields, but as a physical, as hey, this is just 128 bytes contiguous which store information. So, okay. The question is, how do we store this in an LSM tree? Because LSM tree provides a very simple model, just a sorted set of items. So, and here we have just many fields. We might want to have some indexes. We might want to support deletion or something like that. So how do we do this? Okay, so, well, let's start with a simple thing. How do we store a count? And this is done by the so-called object tree. We'll get to see how the entry point, how do we get to this object tree. But right now, think that, okay, this object here is an account. And we are going to put those objects directly in the LSM tree. So I said that LSM tree stores a sorted set of items. So our entire account, our entire 128 bytes are going to be a single item. As usual, when you do something sorted, you need to provide a key function. You need to explain how you do sorting. And for all of our mappings, we have this property that the key is just a part of an object. So we don't store account using some key external to account. The key is actually stored right in the account itself. And object tree helpers type is exactly what gets us this key. Okay, so sorry, I realized that I actually do need to show all three at the same time. So we have this account. This account is the object in this object tree. We use this object tree helpers key from value as a key for sorting accounts, and this is the key. And this is curious because, you see, in this account, we have this ID, and sort of looks like, hey, ID should be the primary key. We want to look up accounts by IDs, so we need to sort account by IDs. But actually, what we do use as a key as a timestamp. So what's the difference here? And this actually cuts pretty deep to the heart of distributed systems. So ID in target-middle's data model is something which is provided by the user. So when a user creates an account, they provide the ID they want to have for this account. The only restriction is that ID is 128 bits, no more, no less, and that all IDs are unique. Now, if you think about it, like how do you actually enforce that all IDs are unique? You might think that you want to maintain some counter, but actually maintaining a counter in a distributed system is a very hard problem, like both in terms of consistency and also in terms of performance, because like you need all your clients, which in general might want to submit transactions and accounts without coordination, to share this globally incrementing ID. So that kind of like just doesn't work. So instead, our proposal is that IDs are generally random. And randomness is cool because if you have 128 bit of randomness, then you can be very sure that two random IDs are actually distinct. And moreover, unlike with just incremental IDs, you can generate non-colliding random IDs in parallel. So all those many clients who submit transfers and accounts to the same target cluster, they don't need to communicate with each other to figure out how to generate random unique IDs. At the same time, once the account arrives at the target cluster, we actually can generate an auto-incrementing ID because cluster maintains consensus and actually solves this problem of like coordinating across many different replicas, and it solves problem of strictly ordering all the events. And this timestamp field is essentially an auto-incrementing ID, except that it also has the semantics that, hey, this corresponds to the real time, because actually it turns out that it's not all that useful if your IDs are densely packed, like it's okay to have gaps in the IDs. And if you store timestamp as an ID, then you get like, extra mileage of this data because you know when exactly this object was created. So that is the idea here. When the user sends us a create account, they provide their like user visible account ID. And internally, we generate a timestamp, which is globally unique, and most importantly, it is twice as small as the ID. Another benefit of a timestamp is that it naturally groups accounts created at the same time together. So if there is temporal locality, and well, usually there is temporal locality, then you can see that locality in the timestamp. So that's why we actually use timestamp is our primary key in the database. Okay, so this covers the object tree. We put this entire thing into the LSM, and we use this timestamp field to actually sort things. So this allows us to look up a particular account if we know its timestamp. Now, what else do we see on this picture? We see this tombstone business. So I guess we'll get closer to tombstones once we start covering indexes, but let me quickly explain what this is about. Again, if you recall our LSM structure, the core idea here is that you have a sequence of layers and for example, if you have mapping like A maps to 1, A maps to 2, and here A maps to, well, actually, let's use some different numbers. A maps to 7, then what is actually true is like this mapping on the topmost layer. But okay, actually we like here we don't store a mapping, we just store account. So let's just say that this is like account. Yeah, let's say that we have like account 8 on level 2. And now we want to delete this account. Now, TigerBeetle actually does not support deleting accounts for accountability reasons, but we'll make use, but let's suppose that we do want to support account deletion. Okay, that's okay, that's confusing. Okay, so TigerBeetle actually does not allow you to delete accounts, but we do use deletion for index trees, which we'll be talking about in 10 minutes. So for now, let's pretend that we can delete accounts and think about how can we implement this in terms of LSM tree. Okay, so we have like this account A and we want like to delete it. The problem is with LSM tree, the only operation we have is that we can only add extra stuff on top. So instead of like delete an account, we add a new entry, which is spelled account. I cannot use keyboard, sorry. Deleted or tombstone. And that way, if you look for account 8 in the LSM tree, you get this tombstone first from a layer 1, and if you get tombstone, you treat it as if there isn't such an account. And you can see how we implement tombstones. So tombstone is the highest bit in the timestamp. And importantly, when we extract the key, we actually mask the tombstone. So an entry with tombstone and an entry without tombstone are going to have exactly the same key, 63 bits of timestamp. But they will be different in the 64th bit of timestamp because tombstone would have this set. Okay, but as I've said, for accounts, we actually don't do this. Like there's no way to delete accounts. Okay, so we figured out how to store accounts, but our accounts are now keyed only by a timestamp. So if you want to look up an account by a timestamp, then you just go in our LSM tree and do this series of binary searches through layers, through index block, through data blocks, which we covered in our first lecture about LSM. But you cannot actually look up account by any other kind of data. And that feels kind of like suboptimal because, well, like users submit accounts with IDs and presumably they actually want to use these same IDs to look up accounts. And this is where ID tree comes in. Yeah, very conveniently, ID tree is right after the object tree. So the goal of ID tree is to store a mapping from a timestamp to the full ID. And this is actually like super simple. So our object looks like this. We have timestamp, we have ID, and we have rest of the fields. So what we're going to do here is let's store it ID timestamp. We'll invent this object, ID timestamp, which is very similar, except that it stores ID first. And okay, yeah, this is key for sorting. We use ID timestamp object, which extracts only ID and timestamp from our account. And here, the sorted field is actually ID. And now we just store two parallel LSM trees. In one tree, we store the entire objects keyed by the timestamps. And in the second tree, we store timestamps keyed by IDs. And this allows us to actually look up account either by ID or by timestamp. If you want to look it up by ID, you do a binary search in this ID timestamp tree. And that gives you the timestamp. And then you can binary search using this timestamp in the object tree. If you want to look up an object just by the timestamp, well, you directly look up it in the object tree. What is magical here is that you can keep these two trees the same. So, for example, if you want to delete an object, then okay, you insert tombstone into this object tree. But when you do this, you also take a look at the timestamp and ID fields of the objects which you are deleting, and you go and you insert a tombstone in this ID timestamp secondary tree. And that's actually basically how databases work. So you see, like, if you look at the relational data model, if you look at those all like joins and products and filters, selections, whatever operations, it seems like, you need like a lot of very fancy data structures on disk to actually implement all this. But turns out there's actually just a single data structure which you need to implement very complicated relational model, and that is just the sorted set of values. Because if you have a sorted set, you could use this construction with indexes, which is essentially a second sorted set just with fields in different order to implement multidimensional lookups. Okay, so let's take a closer look at this ID tree. So okay, yeah. I guess we haven't looked at the table type definition yet, but you like already see that the second argument is what we store the object, and the first argument is the part of the object which is the key. So for the object tree, the entire thing, the value is our entire object, and the key is timestamp, which is U64. For ID tree, the value is ID and value, which is a pair of ID and timestamp. And the key is just a timestamp, just the ID. And this is the function for extracting the key, which, again, just instructs the ID. And for tombstone bit, again, we use the topmost bit of the timestamp for tombstoning. Okay, now I guess the only thing which is left is the index tree. So okay, we now can look up account by ID, or we can look up account by the timestamp. But okay, there is also like other fields in account. For example, user data, which you could use to store some external ID. And you might want to look up accounts by user data. And this setup works, I think, almost identically to this ID tree, because, well, we could store, like, if you want to look up accounts by user data 128, we can store an LSM tree where the value is a pair of user data 128 and timestamp. So index tree is way more comp time intensive, but this is the main definition. So, okay. We want to store an index based on certain field of an object. So if we, again, I guess for transfers it would be more instructive. So we want to be able to look up transfers for particular debit account ID. That means that we need to have an index on this debit account ID field. So this thing is going to be field 128. Okay, so now how do we structure the key? Okay, so our field is an integer, and here, okay, yeah, so this can actually just like, you know, in our data model, our fields might be integers, enums, they might have all kinds of weird bits, but in actual disk storage, we want to boil this down to just simple integers with small sizes. Like, I mean, in Zeek, you could have a field which is U7, for example, but on disk, you want to store at least U32. So this is so this index composite key type function just boils down this type. So for our index by account ID in transfer, we'll get to this int case here, and we'll say, okay, so actually the data which we'll physically represent, which will be indexing on, is 100 and is U128. Okay, and now we fill that into composite key type, which supports only two fields, 128 and U64. And this is exactly, this is stuff exactly as the ID tree. There is this field, and then the timestamp, and the key is okay. Yeah, and the key, and so okay, yeah, that's actually interesting because this is so I was wondering in the back of my head, like, what is the difference between ID tree and the index tree? So you see, in the ID tree, in the ID tree, the key is just the ID part of the value, ID without the timestamp, because we already have the constraint that all IDs are unique. For index tree, it is not actually true that all fields are unique. So if we index in transfers by debit account ID, well, there hopefully are many transfers with the same debit account ID. So here, to make sure that all the keys are unique, we actually need to concatenate the timestamp and the field value. And this is, I write this way because actually the key is like most significant bit. So we first sort by the index and key, and then we sort by the timestamp. And again, the important observation here is that we can keep the object tree and this index tree in sync with each other. So, okay, let's say that you add a new transfer with a particular debit account ID. Then you add this transfer to the object tree, and then you look at the timestamp of this transfer, look at the debit account ID, concatenate them together, and add these to the corresponding index tree. If you want to remove the transfer, well, you remove from an object tree, and then you, again, concatenate its debit account ID and timestamp to get the precise entry you want to remove from the index tree. And this is like where index this is where this uniqueness is very important. So to be able to remove data, we actually need to be able to remove a particular timestamp and a value pair rather than just a particular value, because there are going to be duplicated values with different timestamps. Okay, so this is how roughly we explode something like this into a bunch of LSM trees in TigerBeetle. We create one object tree which stores this whole thing, and it is keyed by the timestamp. Then we create the ID tree, which stores timestamps keyed by IDs. And then we create how many indexes do we need, where we store values we are indexing on, keyed by, well, where we store timestamps keyed by values we are indexing on. And again, I haven't emphasized this, or maybe I have, but that's worthwhile to emphasize this again. Both IDs and timestamps are unique, so we make assumptions that there are no collisions, and we actually check those assumptions when adding stuff to the database. Okay, now how this actually looks at the code. And here we are going to look at some of the mostly horrifically complicated comp time code in the TigerBeetle. So we have forest type. Forest is a thing which stores many groves, and there's this fun thing, forest is bunch of trees. But if you look at the small bunch of trees, you call it grove in English, and I think it is pronounced grove and not groove, but kind of groove is easier to pronounce, and we kind of end up just calling these things grooves rather than groves. So we end up just renaming the thing in the code to groove. Okay, so forest and grooves. What is a groove? A groove is purely logical construct. It doesn't really reflect anything on disk. On disk, there is just a bunch of LSM trees. But logically, we take this single object and we explode it into a bunch of trees. So a bunch of trees related to a particular object is called a grove. So forest. Forest is comp time thing which is parameterized by all the grooves we have. And we have grooves for accounts, for transfers, and then for supporting pending transfers and for supporting historical balances queries, we actually have these two extra grooves. Okay. I guess let's briefly look at the forest type, because there is some delightful comp time thingy going on. I guess the main thing which is stored by the forest is this tree info thing, which is just a flat list of all of the trees. And to build this flat list of all the trees, we iterate all the grooves we have. And for each group, we add the object tree for this group, for this groove. Then if this grove stores an object with an ID, we add the ID tree. So we have IDs for accounts and for transfers. We won't have IDs for posted groove because, we'll learn that once we get to implementation of pending transfers. And then we go, and for all indexes in this groove, we also say, hey, there is an index tree there. Okay. I guess Another thing which is important here is that this tree info contains tree ID, which is a U16 number. And I think we assign those trees. I think we assign those IDs manually. I think constant trees IDs accounts. Yeah. So in this constants, we have assignment of IDs for all the groups. You see, like for each object, we like nonetheless use the same sequence of IDs, and these IDs are unique. So somewhere here we should actually be testing that IDs are unique. Okay, yeah. So this is a code which checks that IDs are unique. And why we need IDs? Because IDs is our type erasure mechanism. So you see that for every tree, we actually have a separate Zeek type. But if you were looking at the manifest log a week ago, you'll notice that this manifest log isn't parameterized by the type of the tree. It is only parameterized by the storage, which is because the same manifest log is shared across all the trees in the database. So you need this kind of type erasure, and correspondingly you need a downcast mechanism. And Forest also provides this, so there is 3.4 ID, which is pretty cool. So you have a forest, you have a tree ID, which is a comp time forest, and it returns you the tree type of the tree with this corresponding ID, where the tree type is what we see here, like this tree type. So it does this like relatively straightforward. It just goes and finds, indexes the comp time list of trees infos with this tree ID and returns its type field. Because again, this whole thing is just basically existed at comp time. So there's like dynamic typing and all that stuff. But what you get is just simple Zeek type. And it's instructive to look at how this function is actually called. Okay, actually, yeah, we've seen this code before. So okay, that's good. So we are looking at manifest log open event. What is this thing? So when your replica starts, it reads this manifest log of events, where each event is, hey, I want to add this tree, this table to this tree, to this manifest level. And this callback is invoked basically every time we encounter such an event. The event is typed erased. So in the table info, we store tree ID as U16, which is not comp time. So here we need to somehow move from this runtime tree ID to a comp time. Here we use Zeek's inline switch. So essentially, this code is if table tree ID equals 0, then we do this thing. And here 0 is like comp time constant. And then else if is 1, then it is 1, etc., etc., etc. So this kind of moves us from this runtime realm to comp time realm. If we didn't find corresponding comp time to ID, then we raise a runtime error that we have encountered an unknown table in our manifest. Otherwise, we fetch this tree and we go and add this table to typed manifest, which is stored in that tree. I guess we won't be looking at the internals of OpenTable right now, because we'll look at the tree type a little bit later. Okay, so that is the forest. And that's kind of like the primary goal of this type is to store a mapping from numerical tree arrays to tree types. Now, let's look at the growth. So, growth. The task of a growth is to take a type and explode it into a bunch of trees. And this is simple for object tree, which is always created. It is relatively simple for an ID tree, which is created only if an object has an ID field. And this is somewhat complicated for the index tree, because it depends on because we want to create variable number of index trees for all the fields. So let's take a look at how it is done. Okay, yeah, again, this is like crazily comp timey thingy. So the first thing we do is that we say, okay, please, Zix compiler, allow us to do an unreasonable amount of comp time computation here. Now, I guess, okay, yeah. First thing we do is that we actually compute the set of index fields we have. And the way this is done is that we actually iterate through all fields of the object. So if our object is account, we'll actually iterate through all of those: ID, debit spending, debits posted, etc., etc., etc. And then we exclude those fields which are ignored. Okay, if the field is not ignored, then we go and append the corresponding index tree. Next, we have derived indexes. I don't think we actually use this yet. Yeah, right. We don't have we don't have a use case for derived right now, but that's an interesting capability, because you might want to compute something. So, for example, I don't know, for account, you might okay, let's take a look at our account. Is there like some interesting okay, yeah. So what if you want to store to index account by the difference between debits and credits? So you want to index account by credits posted minus debits posted. Well, one way you could do this is that you could say credits minus. You might want to physically add this field here and use normal indexing there, but that's kind of wasteful, because this field can be trivially derived from existing credits and debits fields. And that is the observation that you actually have. You don't have to have a physical field to create an index of this. As long as you can deterministically compute some value given the object, you could put that into an index, because again, if you the criteria for what you can put in the index is that you should be able to remove it once you remove the original object, or once you mutate the original object. This is actually important. So suppose that we increment the amount of debits on the account. And we have this credits minus debits index. Well, what we want to do in this case is that before incrementing this field, we take the current difference, we append our timestamp to this difference, and we remove that from the derived index tree. Then we actually update the balance on the account, we compute the new difference, and then we append entry to the derived index tree. So this is for derived indexes. Now we have our object tree and we have our ID tree. And that is our growth. Oh, okay. There are also in-memory caches which I don't quite want. Okay, so let's not talk about caches just yet, and let's not talk about prefetch keys just yet. That's going to be for the episode after the next one. Okay, I guess one last thing I want to cover today is what is this tree type? So let's look at this. We have like index tree type. An index tree type calls the tree type. Tree type is parameterized by the storage, so our grid, and the table. So the table is what is actually stored on disk in a single table. And it's like the table type is like relatively straightforward. I think we actually covered like this entire thing in one of the first episodes on the topic of LSM, because like basically we pass here the key and the value is what defines the layout on disk. So we should be computing what is the max number of values we get. Okay, so what value count max? Okay, yeah, this is it. So kind of like given particular value we want to store in the table, we actually compute the size of, and we can pack block body size divided by value size items in the table, and that defines the topology of the table. So that's kind of like the main thing why we need parameterized table, because we just depending on the size of value, we can pack only so many values in a single table. And then of course we also are going to binary search tables, so that's why we add all the functionality for binary search. Okay, so and that we pass in the tree type. And tree type, the main thing, so tree type is actually that sorted list of layers. And the main job of a tree is actually to coordinate access to all the tables all in different layers. The key data structure inside the tree is this manifest. So this is important. Manifest log is only parameterized by the storage, and we have one manifest log for all the trees in our data file. However, manifest type is parameterized by the table and storage. So we have manifest type for each particular tree. And actually, I think that's going to be a good good place to revisit this. Open. Not manifest level, manifest log. Open event. Open Where? Okay, so I want to. Okay, where was it? Uh, I, I like I want to find that thing where we call the callback when we open the particular block. So okay, we have this entry, and for each entry we call open event. Okay, open event is a callback. How do we? Okay, so I guess it is going to be in the forest. Okay, yeah. Okay, so it was in the forest, not in the manifest log. Yeah, so this is called for each untyped entry in the manifest log. And we call open table inside a tree. Okay, yeah, we call this table. And here, we actually should be tree ID. We should be certain that table tree ID equals our tree ID, because our tree ID, I think. Oh, right. Okay, yeah, I think actually, yeah, this is. This is funny because trees do not know their own ID, so that's why we cannot assert here that the ID matches, and we actually don't want trees to know their own IDs because we want all the trees to exist independently. Because, like, I mean, our IDs are global. So if, I don't know, account object tree knows that its ID is 5, then it implicitly depends on all those 5 trees before it. So we actually kind of like just trust here that the ID is the same. But anyway, here we take this untyped table, we decode it into type table, so into like the table which is for this particular tree, and then we insert this table into our manifest, which is based on sorted segmented arrays. Okay, so I guess this is a good point to make a pause here. I apologize if this video was way more comp time heavy than it is like reasonable to expect to be sane. I mean, actually, like I don't think we've discussed like like this tiny thing about opening trees was actually happening at runtime, and this is like the only place of like runtime logic which we have discussed today. Everything else happened at comp time. So to recap, we learned basic primitive log structured merge tree, which is a sorted set of values. We want to use that primitive to store our domain objects. We used three, the trick here is that you take your single domain object and you map it to several LSM trees which exist concurrently. Specifically, for each object, we create one object tree which stores objects themselves keyed by their unique 64-bit timestamp. Then we store ID tree, which stores timestamps keyed by unique 128 object IDs. And then we store for selected fields of an object index trees, which stores timestamp keyed by not necessarily unique value of the field we're building index of. As a result, we have an on-disk data structure where you can look up an object by its timestamp, by its ID, or by any of the fields we have indexes over. And in terms of implementation, that's just a giant pile of Zeek's comp time. Okay, I think that's it for today. Now, next time is going to be a surprise episode. It's going to be technical, but technical in a different way than today's episode. So the next episode we are going to go on a like very philosophical tangent about how you actually write big software, how you can engineer the culture, the company, and how you like pursue this collective endeavor of like building software. So if you are interested and like these kinds of like fireside philosophical chats, then the next episode at 5 p.m. UTC on Thursday on Twitch is for you. Otherwise, if you are here solely for Code and Zeek, then you might want to skip the next episode. Okay, so see you next week, and then the week after that, and then the week after that, and then at least until we've finished with Tagabidal, which I'm not sure is going to happen anytime soon because, surprise, while we are discussing Tagabidal, there are actually new, interesting, exciting features being implemented on top of it. So, I mean, like we have to cover scans at some point, which I don't think are present in this version of the code, but which are already in the main branch. So thanks for watching. Thanks for listening. Hopefully your brains aren't completely melted due to all of the comp time things. And see you next week.